to do this talk. This is great. Last year, I think everyone heard from Max and Tim from our lab, so I thought this year I would step up and do the talk. So my topic is about using space around us for immersive analytics. So we're going to talk about several projects throughout that I've worked on over time. So first of all, I guess very briefly, what is immersive analytics? So this kind of comes from the concept of visual analytics, which is about supporting human-in-the-loop decision-making. And you have a lot of setups like these multi-computer environments and very large screens. And more recently, people have been exploring how can we make use of these immersive technologies to support sense-making. So you have potentially unlimited display space to put things around you. And you have, kind of more natural interaction, or at least spatial interaction. And this was kind of the topic of my PhD work I called spatial analytic interfaces. So thinking about how to leverage spatial interaction to kind of support more effective interaction with immersive technologies and kind of putting information interacting with information in the space around us. For instance, in this kind of envisioned kind of control room scenario, you can take the control room with you to the work site. So this, all of the work I did then was inspired by some work from Mark Billinghurst, who did this project in 1998 about it was a user study on augmented reality showing how you can use head switching to kind of move between applications more quickly. So rather than, at the time was mobile devices and smartphones were becoming popular when I was doing this work, and people were inventing, multitasking became a thing, and there was this kind of overhead of switching tasks on a mobile device. And, this work shows how great it would be if you could just kind of have these applications floating around and you can just kind of move from one to the other simply by moving your head around space. And this kind of became the topic of this project I did then called the personal cockpit. So kind of explores this kind of multi-display layout and physical space. So kind of took this to a bit more extreme where you have this kind of 2D configuration. The idea is that everything would be within arm's reach. And thinking about, display technology, you might have roughly 40 degrees field of view, and how can you kind of move between these applications with this limited field of view of AR technologies. So similar to, I think Bruce mentioned this in the talk on Tuesday, is a limitation of AR technology, earlier AR technology, where studies were limited by the kind of latency and so forth of the existing technology. So this was before we had HoloLens and Oculus was in very early days. So we kind of did this simulation using a cave environment. So we had a very low latency Vicon tracking system and this cave display. Said, why don't we apply this to see what we can do to do some kind of evaluation of head switching with these multiple displays. So I designed this, what you might call an analytic task that required the participants to switch between these different applications, and they had to solve a problem. So I created two kind of baseline interaction techniques where you had to kind of switch from one to the other. And the main result, you can see all the details in the paper, but the takeaway was that head switching was about 40% faster than the baseline techniques that I had implemented. So there is some kind of clear benefit of being able to switch just using head motion, using natural interaction. So this is also related to some early work from Steve Feiner in 1993. He published this paper on Windows of the World, and this was talking about how you can put these virtual windows and attach them to different objects. You can have them kind of in space around you in what you call the surround, or you can fix them in the world so that they don't move when you move. And I was thinking about how do you transition from one of these to the other? So with this personal cockpit, we thought, well, what if you could just take your windows and drop them off on the wall before you go out for lunch? And when you come back from lunch, you can pick them up again and you can go on with your work. So it's kind of a cool concept that I explored in my follow-up project. But I thought about, well, what happens if you have these different environments? So in the example I showed, you have this nice plain flat wall, but our real world environments aren't like that. You have all of this geometry and there's things. And how do you fit these windows in around these objects? And more importantly, how do you maintain consistency of those layouts between these different environments? So say if you have your office and you have a living room, how can you, where do you put these windows where you kind of maintain the kind of order of the windows? You want them to be relatively in the position where you expect to find them. But you also want to avoid putting them over top of important objects in the environment. So, or covering up things that you want to have access to in the real world, right? You don't want the virtual things to just take over your whole view. So we kind of created this window manager that used kind of an optimization algorithm based on these scans. So we had so shortly after Connect Fusion became available. So we took some scans of these two environments in our lab, Connect Fusion, and then we overlaid some visual saliency map. So we used a method from Bruce and Sotsos. And this in this map, you see the light colored areas are areas where there's salient visual information. So we want to try and avoid those areas. And then you can overlay this saliency map on the 3D structures. You see the red areas are the very high salience. So we want to aim to put stuff in the green areas. So it's kind of a random walk algorithm with various factors like the order of the windows and the relative position, and the saliency and the geometry, trying to avoid edges and so forth. And this is the layouts in these two different environments. And this is what it looks like. We're using the Epsilon Moverio device at the time. So this is tracked by a Vicon system. And this is what the layout looks in the first. And this is the same layout in the second one. So it finds these kind of flat, empty areas to put stuff for you, but trying to maintain the relative configuration between things. So moving on to some more recent work. This is a project from one of our students, Joe. I think I saw him come into the audience. Hi, Joe. Joe's PhD is about small multiples visualization. So small multiples, if you're not familiar, is a visualization technique where you have a set of visualizations that have the same visual encoding, but you alter one of the variables. So in this case, the change in variable is the date. So you have this layout of these different architecture or these different kind of building systems. So this is a air conditioner data, I believe, in these different kind of building models over time. You can see the differences as you kind of scan across. You can see how are those sensor data values changing over time. So I think it's the temperature data that was detected inside those buildings. And so Joe created this design space for the spatial layout. So applying this idea of the kind of a cockpit-like interface, what are the different configurations? So you can have 2D or 3D, you can have flat or curved displays in different directions, different aspect ratios, and so forth. And again, I'm covering this at a very high level. And you can look in the paper for details, but Joe, we were looking at these kind of, how can you apply this with different data sets? So of course we think, this is going to be more useful, and immersive small multiples will be more useful if you have 3D data. So he's looking at these different potential data sets like aircraft trajectories, BIM models. So we were doing some work with Honeywell at the time, and they're very interested in BIM information, and just more abstract data like a 3D bar graph that has the kind of demographic indicators of different countries. And so Joe used this shelves metaphor where you could actually kind of grab the shelves to manipulate the display. So you want to be stuck with one configuration. You can do things like bend the shape of the shelves, or you can kind of move from the posts and change the aspect ratio of the shelves, or change different elements of this design space. And we also looked at interaction with the data within those individual visualizations. So doing things like rotating the visualizations, or doing some brushing of the axes or brushing of the objects for selection and so forth. And after implementing all of this, we ran a comparison study. So this required participants to kind of, we would identify two particular visualizations out of this grid, and they had to kind of solve some problem where they had to make a comparison between these 3D data visualizations at different locations. And what we found was we measured a few things. Again, you can look in the paper for all the gory details, but the takeaway from this first study was that the quarter circle layout, we found this had a faster completion time than the others. So it was kind of the middle, the sweet spot between the flat and the half circle, which was interesting. Then we decided to scale this up and see what happens if you make a much larger set of multiples. So we only had a smaller number. We said, what happens if you have many more multiples? Do you kind of have similar results? We also replaced the quarter circle with the full circle, because our first study didn't have the full circle. So you have things like our K2 environment that we used to have at Monash that has this kind of full circle of displays around you. And it kind of makes sense to be able to just turn around and find things that you want, but how does this compare to these other configurations? And so a similar study, we had a comparison task. They had to look at two different visualizations somewhere in this array. We didn't find any performance differences, but what we did find was that participants preferred the half circle. So again, kind of the sweet spot between the two was the most preferred by participants. From qualitative feedback, people said that the full circle layout was disorienting. So it was harder to find the visualizations they were looking for. So when they're doing the comparison between the two, it was more difficult to kind of identify the one that they needed in the full circle. And the flat is nice because you have this full overview. So you can kind of back up and see everything at once. So it's a nice advantage, but then you're far away from them and it requires more walking. So when you want to go and interact with them, you have to walk to get closer. So there's a potential time and convenience trade-off there. So some really interesting results on these different types of layouts. And this is a related project. So another student of ours, so Kadak, he's just about to graduate, and he's actually trying to get his permit so he can move over to Adelaide. He's going to work with Bruce Thomas on a project there. But this was a project he did as part of his PhD at Monash, looking at multi-view map layouts. So a multi-view map is essentially it's kind of an organization of maps in this hierarchy where you want to solve a problem where you require the use of different scales. So you have this big overview map where you can kind of see at a high level, and then you can kind of have these different detail views that come out of the map, and you can kind of have any number of these. So this creates a hierarchy where you can have one detail view, and you can pull out another view from that detail view and have even a different scale. So you can have all of these multiple scales that allow you to kind of, for certain problems that you need to be able to look at things at different scales. So this applies to other things, other data sets other than maps as well. But in this case, we're looking at multi-view maps. Here's an example of this prototype system that Kadak built. And this is the idea of how it works, is you can kind of select an area, pull out one of these maps. Again, you can make this into a big hierarchy, interact with the maps. And then while I was building this, we realized, it was a big question is you very quickly get this proliferation of maps, and where are you going to put them all? Where are these maps going to go, and how are you going to organize them? So similar to Joe's questions about the layout design, this is a bit more freeform. So you kind of have more control over where you're going to put the maps, and how are users going to organize these? So what we did was did an observation study. So we invited 16 participants to come in and interact with a set of maps. So we kind of had this preset set of maps. They weren't really interactive. They couldn't pan and zoom. The maps were just kind of there, and we just kind of asked them to organize these through a set of different tasks. So given this set of maps, how would you, where would you put these maps for these different sets of tasks? So I had to work through each one of these tasks and create a map configuration. So in total, with these participants, 16 participants, and these 5 different tasks, we had 80 different layout configurations. And Kadek did a great job of analysis. You basically did kind of an inductive analysis. So we looked at these and tried to organize them and see what he could find. And these are kind of the key findings. So first of all, the geometry. So people tended to create these kind of spherical things. And I mean, this is partly, I think, due to how you design the interface and how people can manipulate things. But I guess in, when you're using kind of direct manipulation, you have a tendency to kind of grab things and you put them kind of at arm's reach around you. What was interesting was not everybody did this. Some people tried to keep to this planar configuration. Some people used all of the space around them. So similar to Joe's like full circle display, we found that most people didn't use that full space. They actually kept it to a limited amount of this space that we call a spherical cap. So it wasn't a full sphere, it was kind of a piece of a sphere. And they found this was much easier to navigate than using all of the space, the surrounding space. And he also found some interesting patterns in this, what he called overview detail relationships. So again, you had this main overview map and you had all of these different views like that. And a lot of, so some people put them in this central window configuration. Other people created what kind of called a coordinated layout. So you have the overview on one side, and then you have all of the maps kind of in rows or some pattern off to the side. And then some people created this kind of occluding layout. And I'm not sure what the strategy is there, but they had some people actually created, put windows in front of one. So maybe they're trying to create stacks, I think, is they're organizing them in stacks, which is actually interesting. But the majority of participants kind of followed the first pattern and created this kind of central window. So they would have the big overview in the middle, and they would place everything around that within this spherical cap. And he also noticed some interesting patterns in the way people approached the tasks. So some people just organized all the maps and they left them there, and they did this at the beginning of the task, and then they completed the task in the second part. But other people actually used the positioning of the maps as part of their task. So this was actually part of the thought process. So they'd make an initial layout, and as they were thinking through the task, they would move the maps around, and this kind of physical manipulation of the maps became, kind of an integral part of the task, which I thought was really interesting. So some great results there about layouts. So I think there's some kind of similarities between these about some parallels between these layouts in Joe's work and Kadek's work. And there's some other studies, like Immersive Space to Think by Chris North and some other works that have kind of found similar patterns about these kind of configurations. And I think there's more work to be done in this area, but this is some great interesting projects that have started answering these questions about immersive layouts. So I'm switching gears slightly here to a different problem. So other than maps and other types of data, one of the uses of immersive space is to potentially look at data about things that are already there in the environment. So these kind of smart buildings are becoming a lot more common. We have our new kind of Woodside teaching and learning building on the Clayton campus, which Erwin mentioned. This is where our new VR lab is. This has sensors all over it. There's other buildings that have, Internet of Things enabled devices that you can control remotely. And with AR technology, wouldn't it be great if you could just go and see all of the information about these within the context of that environment? right? So often we have these kind of desktop dashboards where you can see the data and monitor things, but that's kind of limited use. Wouldn't it be nice if you could, have the context of that spatial environment and the data in the same place? So it's kind of the motivation behind this project I call ARIVE. So this is some work that I did during an internship at Autodesk Research in Toronto. And ARIVE is essentially it's a spatially situated visual programming environment. So it's about authoring constructs and understanding connections between smart objects and visualizing the data flow between them. So I created a visual programming interface based on this concept of nodes and links. So the nodes are things like, so a port is basically your input and output of a smart object. So it's a kind of an embodied representation of the connection to that object. You have a trigger, which is kind of a standard, IoT. If then that operation was kind of the most obvious and common thing that you would want. If you turn, if some condition meets, then something turns on or off, for instance. There's a bunch of different kind of various operations that I won't go into in this talk, and sending data into the cloud, I guess we thought was important as well. And then we had this concept of tubes where you could place these links and connect them to objects and connect everything together with this kind of tube metaphor. And in this demonstration, we want to show that you can actually take physical input from sensors. We use these TI tags that just, these little things that have some sensors built into them, and use those as inputs to the system. And we had physical outputs. We actually wanted to have some actuators. So you have the whole workflow of sensor data through the programming environment actually affecting something in the real world. And we also want to show data flow. So how can you visualize this data as it's moving around through this program constructs? So you can kind of debug and see what's happening and what's going where. So different types of data were encoded by different colors and so forth. So here's a very simple example. So we had this training room when we did our evaluation of this that I would use. This is kind of tool belt. So this is a trigger node. So I just place the trigger node in space. And then I take the linking tool and I'm connecting this light sensor by the window to the linking tool. So that's the sensor data going into that trigger. And then you can kind of modify the parameters. The GUI isn't pretty, but there's some things we didn't solve everything in this project. But then the interesting part is you can take that trigger output. So if a certain condition is met, if the light is over a certain value, then it's going to turn on this fan. So if you look in the lower right-hand corner of the video, I'm going to press run, and here's one of the TI tags I mentioned. So I'm going to shine a flashlight on the light sensor, and then you can see the data values change, increase, and lo and behold, they activate the trigger and the fan turns on. So we actually had a physical fan in the lab that actually would turn on when this happened. So that was quite cool to see the actual physical result of this, and that's another example. Of course, you can build much more complex programs. This is an example of something like a museum where you might be able to use, of course, we were working in VR in this project, not AR. So imagine if you could remote into this environment and you could kind of inspect the traffic flow and look at the sensor data of what's happening, so forth. So in addition, once the program is built, you can kind of inspect things that are happening there. And there's also a set of debugging tools. So you can see this data coming through the program, but if there's some problem, you can, there's tools like a step, a line step program. So you can step through each node one at a time and, try and see what's happening, so forth. So it was a really fun project. And I think it kind of leads into this project. So this more recent project, which is another thing that came out of our lab at Monash. This was led by Arnaud Prouzeau, who's now moved on to INRIA in France. But while we're here, as I mentioned, we're working with Honeywell, and we're very interested. They were interested in visualizing BIM model data. So BIM is building information models, which there's a representation here on the left. So this is essentially one of our rooms in, it's called the TED building on our Monash campus. And this is the AC ducts and things that are flowing into there. And on the right is basically a 3D photogrammetry scan of one of the plant rooms, physical plant rooms in our environment. So we have these kind of things to work with. We have BIM data. We have these kind of realistic looking 3D scans that are available. So how can you kind of put this together? So we came up with this concept of an authoring tool. So the Corsican Twin, of course, is, I should mention this is named after the book, The Corsican Brothers, which was a novella published in 1844 by Alexandre Dumas. And the concept of the Corsican twins is you had two twins where one twin could feel the other's pain. So in a similar sense, we kind of had our digital twin, and we have two kind of versions of this. We have so there's actually three things here. So there's reality, there's the physical environment, and then we have a virtual environment. So we can kind of go into that 3D photogrammetry scan, and you can use this in VR, and you can kind of go inside it. So you have this kind of realistic looking representation of that room. And then you have augmented reality. So the idea was to, if you want to be able to see data from sensors that are in an environment, at some point you have to decide where do those data visualizations go? So where do you put them? So in this workflow, we imagine that you have a designer who can kind of author these data visualizations in the virtual digital twin environment. So they don't actually have to go to that environment. They can kind of see what it looks like. They have access to all of the data sources and the sensors, and they can kind of decide what does the user need to see. So what is the use case? What data do they need to look at? And link these data visualizations to physical objects and situate those data visualizations in space. So the idea is you would create this all in the virtual environment using this authoring tool. Then you would place something like a marker. You need to, I guess, essentially align those rooms. So you can do this quite well just by using a single QR code marker. You place this in the real environment, and then you go in with your HoloLens. So actually place this in the virtual environment. So you take the QR code and you place this where you want, basically anywhere in the virtual environment. And then you place a real QR code at the same place in the physical environment. And you essentially load up the project, and now your building technician can go in and interact and view these different data visualizations. So we built this tool to support some different types of data visualizations. There's a bunch of things you can author in there. So this is building on the work of Willett, who created this design space for different types of visualizations. So we're mostly interested in this middle part, where you have situated visualization, which is defined, at least in this framework. A situated visualization is a data visualization that's spatially situated in 3D space. And the point of doing this is you have it near, in the area of interest. You kind of want it to support the worker's tasks. So you put this visualization where it's useful. And then embedded visualization, according to this taxonomy, takes that a step further. So as in this picture of this kind of a mock-up of a grocery store shelf, you have the data encoding actually physically embedded onto the objects in that environment. So you have this kind of one-to-one relationship between the data encoding and the physical object that the data is related to. So that data object we call the referent, and the referent has some sort of data source, and you kind of make a very close coupling between those things. And the idea would be to make this much more intuitive. So we supported both of these in our tool. So here's, so what we didn't include everything, of course, but what we had was some ability to put some line charts and bar charts. Mainly this is temporal data, right? So this is data coming from the sensors. We're looking at real data from this plant room that we got from buildings and properties. And this is mostly temporal data. So we have these temporal visualizations of the data, like the line chart that you see here. And then the embedded visualization, and there's a few interesting steps here. So you link the sensor and you have to define the physical object because we didn't have that, in our model. I guess in some BIM models, they might define some of the physical objects and the locations for you, but in this authoring tool, you can kind of take the cylinder and place it where you want it. So that cylinder isn't magically there. The author kind of has to place the cylinder where they want the visualization to be. And then you can use different encodings, like we looked at color and a size. So you have an animation where the size changes depending on the data or the color changes. But it's, so while this is potentially more intuitive, you're only going to get kind of a snapshot. So you're going to get the instantaneous value of that sensor, and potentially you don't get all of the overview of the whole time series that you get with the situated viz. So there's potential trade-offs between these, but in this case, we figure, okay, it's up to this designer to decide what does the operator want to see and what's most useful for them to see, and what's the most useful encoding for them to see that. So the tool, the aim is flexibility here. This is just a little snapshot of the authoring tool in VR, and that's placing the marker in VR. And then this is the HoloLens view. So you scan the marker and you see all of these data visualizations situated in space in the plant room. And there's a combination of situated and embedded visualizations there. Again, there's more details in the paper. I'm going to move on to the final project that I'm going to talk about today. I'm actually impressed I'm getting through these slides much more quickly than I thought I would. So this is a paper presented at CHI last year called Grand Challenges in Immersive Analytics. And this was kind of an interesting collaboration between 24 authors. So I had to include an extra slide to fit the author names on here. So this came out of a workshop the previous year at CHI. So we actually had two workshops. We had one at CHI 2019 as well, and CHI 2020, and these were kind of immersive analytics themed workshops. And in this one, we were, the output of this became this Grand Challenges project. So what are the big challenges in immersive analytics? So the field has kind of like grown. It's still a new field. Looking at these emerging technologies, but it's kind of flourished over the last, say, 5 years or so. There's loads and loads of work. So part of this paper was building on, there's a previous survey of immersive analytics work, and we kind of filled in the gap of the last couple of years. So there's a good overview of recent work in the field. And from, a series of discussions, of course, this was all online during COVID. But we had some group discussions, and we kind of came up with this set of 4 topics and 17 kind of new challenges within these topics. So I'm not going to give a complete overview. I'm just going to talk in particular about 2 that are related to this idea of situating data in space around us. So these are challenges number 3 and 4 from the paper. So number 3 is designing guidelines for spatially situated visualization, and number 4 is understanding human senses and cognition in situated contexts. So I think these are both related to one another, and they both kind of tie into this chart that I've shown here. So this is from the paper. We call it the spatially situated visualization continuum. So you can take some different works from over the years. So there's many of these kind of predate immersive analytics, like visual analytics, and you can kind of place them on this continuum of support for spatial interaction. So this is what I mentioned at the kind of beginning of the talk, is being able to use things like head motion and kinesthesia and proprioception and spatial memory, and kind of take advantage of those for interacting with information. So you see spatial analytic interfaces at the top, which I mentioned previously. And then on this axis, you have this kind of integration with the physical reference. So remember the framework I mentioned by Willett, and you talk about situated versus embedded visualizations. So at the far right, you have embedded data visualizations that really have this very tight coupling between the physical realm and the digital realm, or the information realm and the data. And this is just kind of a thought experiment to kind of situate these. And I think there are other dimensions. This isn't really, I think there's more exploration to be done here. But I think what is interesting on both of these axes is kind of an outline of some future work. So on both axes, there's a lot of assumptions. When you read about immersive analytics and situated analytics and embedded data representations, there's a lot of assumptions that things like spatial interaction and that integrating data with data visualizations with physical reference, there's assumptions that these are going to somehow support our ability to make sense of the data or make sense of information. And I think there's some basis for this. There are a fair number of studies that have kind of looked at support of spatial interaction. So the work that I mentioned by Billinghurst and the personal cockpit really show that there's some advantages of head motion. But there's, we don't have a complete picture of that yet. So how does embodied interaction really support sense making? I think it's kind of an ongoing task, and we need a large collection of studies to really demonstrate this, and more targeted studies in future. And likewise on the x-axis, so this assumption that integrating data with the physical referent, as I showed in the Corsica Twin project, there's some potential trade-offs of these. So one might be more intuitive to have this embedded representation, but maybe you have a more limited, we call it like a bandwidth of information that you can see in that visualization. So maybe it's more limited in terms of what it represents. So I think there's a lot of room still to explore, and what are the benefits of those different trade-offs, and really empirical evidence that shows, that kind of solves our intuition. We have this intuition that these things are beneficial, but we haven't really shown that definitively yet, particularly on this x-axis. And I think there's a lot of interesting work to be done there. So that's my, I guess, my nugget of wisdom for the end of the talk, and let's bring it full circle back to my title slide. And that's it for me. So I guess I didn't introduce myself at the beginning. I think I know some of you, but if we haven't met, I am Barrett Enns from the Data Visualization and Immersive Analytics Lab. So a lot of the projects that are discussed came from this lab with many of my colleagues and students there. So thanks to them as well for being part of this presentation. And thanks everyone for watching.
I'm not sure.
Thank you,
Alex,
Barrett.
Yep.
Yeah, I was trying to figure out how I can open up without messing up with the recording. Thank you, Barrett. And as always, we are open for questions. We have about 10 minutes in our schedule. So any questions from the audience, you can just unmute yourself or use the raise hand.
I see no one except me unmuting, so maybe I do a start. Even though it's a very general question, but I'm actually really interested in it. So some of the, or actually a lot of the stuff what you do, that almost seems like very close to a product somehow. I mean, I immediately see the potential benefits. We had the one with the building information model or the connection of Internet of Things and so on. So what from your perspective is really missing? Is it like that we need more AR VR devices, or is there something in the fundamental principles that is missing? Because for me, it really looks usable. I'm kind of convinced.
Yeah, well, I think it's both. So coming back to this grand challenges paper, I think it's far from a complete set of challenges. It's kind of like the musings of this workshop, and it's a good list of things, but it's very broad. So the overall topics are interaction, evaluation, this kind of spatially situated stuff. And the fourth one, I believe, was users and there's users and evaluation. So I don't remember the fourth one off the top of my head, but so there's a lot of different challenges about multimodal interaction and how do we evaluate these systems and show their benefits. And I'm particularly interested in these kind of questions about putting stuff in physical space and how is that going to affect, I think it's great to kind of get rid of these little glass boxes that we carry around and have on our desk, but how do you actually work with information when you kind of let it out of that box and you have to integrate it with physical moving living things. So I think we're a long way from this being useful. I mean, there's a lot of industry interest in these areas, I think. I'm not sure anybody is using this stuff yet. In particular, I think we're much closer with virtual reality. So virtual reality is, if you, as I mentioned, there's kind of flourishing in immersive analytics, and this is the vast majority of this is in virtual reality because it works really well. So you can kind of plug it in. There's not a lot of work to get it working. It just kind of works, and you can do stuff with it. And there's all these toolkits coming out to make immersive analytics a lot easier. So I think the applications are they're more closer to being ready in that space, I think. But for me, I think the more useful stuff is when you can take this out of the VR environment and put this in real world space. And I think this is where some of the advantages, at least for me, I think this is what's always interested me more about immersive stuff is putting information in the real world and interacting, kind of this kind of vision of ubiquitous computing, right? Like having this invisible computer.
Yeah, but then of course, then you have the problem for this VR. I think that for me, I think it's the big or maybe the only problem is that everything then needs to have the data exposed and located, right? You need that data somehow. It's there, but then it introduces all these privacy issues. Yeah, so that to utilize the real power, for example, from AR, then every building, every object needs to be smart in somehow a way.
Well, it needs to be smart, but you need to also know where it is. You need a map of that data. You need to somehow register those objects. And beyond that, I think just the technology doesn't work as well yet. So we have these HoloLenses, which are amazing, kind of a miracle technology, but you don't see a lot of people using them outside of research labs because we just don't have support for like large scale tracking and access to that data, like integrating that with our building systems and actually getting that data. Having the data there is one thing, but getting it into an AR system is a whole other issue. So there's a lot of kind of infrastructure problems. And you're right, there's privacy issues, there's social acceptance issues, there's contextual issues. So different, how to use these technologies in different relationships, whether it's work or at home. And it becomes very complex. You have moving objects, you have forklifts driving around that can crush you, and how do you deal with all of this? So I think the first step is kind of building more technology support to enable it, and then we can kind of start solving some of those more complex human-related problems. I see Erwin has his hand up.
Yeah, I'm a bit more pragmatic than you guys because I come from a clinical background, and I know that the digital twin phenomenon is really good in engineering and in big industries because they can't afford to build an aircraft engine and have it fail on the day. So, but coming back to health, because that's a changing dynamic at the moment, obviously with pandemic on our doorsteps, workflows are changing constantly, and we really are playing catch up all the time. It'd be good to see where this sort of approach could be used to help plan for future pandemic events. How do you rearrange a physical building or rearrange workflow? And for Barrett, at our end, we've got the Victorian Heart Hospital being built at the moment. Now there's going to be obviously labs there. There's going to be simulation centres there, workflow issues, fitting it out. What technology is coming down the pipeline that we haven't even thought about yet? I think there's great opportunities for it to look at this as kind of a translational approach to how do we do it better this time and don't cock it up like we did last time, if you get my drift.
Yeah,
I'm being quite pragmatic here.
well, there's certainly no shortage of opportunities. So I think a parallel is when we're working with Honeywell, they took us on a tour of this building in central Melbourne, this hospital building, and they said there's something like 80,000 data points that they have connected that they're monitoring through their systems. So most of this is automated, and they have alarms and things like that, and they have a control room with a half dozen or more people kind of looking at this at all times. And it's, I think there's a lot of huge problems. So I think where we are now is we have cloud storage, we have devices that can collect, we have sensors. All of this is very cheap and easy to install. So it's easy to collect loads and loads, gigabytes and terabytes of data. But the problem is now, what do we do with this data? And the capacity just isn't there to handle it. So I think part of this is market issues. So there are all of these ecosystems. So every supplier has their own ecosystem, and they don't make data. They don't make money off of the sensors. They make money off of the tools that they want you to use. So the license from the software to analyze their data, and there's a cross compatibility issue. So all of these different sensors, if you buy sensors from one company and some other sensors from another company, you're not necessarily going to be able to integrate those and see the data from these. So just, there's I think a lot of, and beyond that, there's all these barriers of just, if you do have access to the data, how do you make sense of all of that data, right? There's so much of it. And you can bring in some, the thing I didn't talk about here is using machine learning and AI and data mining and all of these things to help, which is kind of part of the concept of visual analytics, right? As you have this pipeline that's integrating this human in the loop, is putting the human in conjunction with all of these other kind of smart technologies that we have to fill in that one piece. But
yeah, I might just
I think we lost him.
I think so too. Well, it is unfortunately also about time that we have to close, and I actually have some more questions, but I will leave them for the panel discussion that I hope you will be able to join us in October.
Sure.
So at this point, thank you everyone again for joining. Thank you, Barrett, especially for the talk, and we will see you all on Tuesday. And I believe it's Heide's talk. Great. So thank you all again, and we'll see you on Tuesday.
Thanks for organizing.
Thanks, Barrett.
Thanks, everyone.